through this today, so hopefully we will not take that much time like yesterday. So I hope it will be faster. So let's start. And then after I will ask you questions. If you have any questions, we can answer these afterwards regarding your projects. All right, so we will look into these topics today. Okay, let me just try to open myself in a different window. Just trying to arrange everything so I could see if you have questions. Okay, that's good. Okay, so let's move. So exceptions in many programming languages are essential things. Exceptions are special objects that are being thrown on exceptional situations, right? So when something weird, something unexpected happens, exceptions are being thrown up in the stack. So basically, the stack is being constructed when we call method after method. So for instance, in this example, we are starting our Java application from main method, obviously. Somewhere there is a main, even though you have not programmed it, but from operating system, the entry point is in the main method. So basically it starts from main, then you call a method, then another method and another method. So this is how you actually build the stack of your calls, right? And so it's being built up. It's not unlimited. It is limited in the size is limited. It is specified by the virtual machine or by some parameter. I think in an example, we will look into this and we will see what's the stack size for my machine. So there, once in some kind of method, once the exceptional situation occurs, happens, actually the method can throw the exception. So basically, a new object of type exception or throwable is being constructed, and it's being thrown back down the stack. Actually, yeah, down the stack. So basically, exceptions being thrown back and back until somewhere there is a block. There is a block which actually handles that exception, waits for the exception, and then exception can be handled or taken care with. Sometimes exceptions are so severe, so unhandleable that they are actually go down to the main and crash the whole application. So we will take a look into various occasions. So there are three types of exceptions. So we have so-called checked exceptions, errors, and runtime exceptions. So checked exceptions are the ones that are actually need to be handled, and they are so-called common exceptions. So they are here. All the descendants of exception object from the virtual machine API are called checked exceptions. Errors error is the special kind of an exception. When something unhandleable and not possible to handle, unrecoverable, actually happens in the virtual machine. So error is being thrown. And runtime exception is the type of an exception which does not need to be handled explicitly. Okay, so here it said errors and runtime exceptions are collectively known as unchecked exceptions. Yeah, so basically we have checked exceptions and we have unchecked exceptions. For the checked exceptions, you have to declare throwing and handling in methods. But for errors and runtime exceptions, you are not required to handle these things. Okay, so here's an example. What we have a method, right, which says read file, right, and it throws sample exception, right, throws sample exception. So basically this throws sample exception. Throws a sample exception. This method, somehow it's said function. I think somebody has modified my slides a little bit, right? Okay, so this method actually says that throws sample exceptions. So this is a checked exception, and the sample exception need to be declared if somewhere within the block of this method actually throws an exception. This is inside the method. We have a block, try and catch block, so-called try and catch block. So within this try and catch block, we can have some other methods called that can throw these checked exceptions. So something like a file not found exception, which is actually IO exception, can be thrown. So if somewhere in these lines, in a block, in the content of a block, file not found exception is being thrown, so most probably this is a file reader that would throw this, right? So basically this block will take care of this exception. So it will receive variable E, and this E will be basically will handle information about the file not found. Anything relevant to the file not found exception, this situation actually will be displayed over there. So within that block, you can see that there is a line that throws new sample exception. So basically, this line throws a sample exception. That's why it is a checked exception. That's why we need to declare that this method is about to throw the sample exception. Other kind of IO exceptions in this block are being handled in this block. And so for the example, we have a finally block, which actually is being executed regardless of the successful or unsuccessful execution of the block. Okay. So basically, these are the questions that I would ask you in a class. Would this A compile, and what it would print? So basically, this is a block. Maybe you can answer me in a chat box if A would compile and what it would print. What's your opinion? You can write in the chat or tell it by voice. Okay, so the trick here is that it would not compile because this block requires to throw IO exception, and this IO exception is a checked exception, and nothing actually throws IO exception. So this block would not compile, because in order to declare the handling of the specific exception, checked exception like IO exception, requires that some line, some routine actually throws it, right? Which is being called within the block. So nothing is being, nothing throws, none of these lines, which actually we have one line on in the block, right? Throws the IO exception. That's why it will not compile. It will say that this is an error. You have to call a method inside this block that would have declared IO exception as being thrown. Okay. Second example, would it compile and what it would print, right? So try block, nothing in this block, and there's the block of catch exception. So in this block, you can see that there are no lines. So obviously nothing is throwing anything, but the super type of exceptions, so ironically, can be declared, right? Since this is not some specific catched exception, it can be declared like this, right? So this is not specific, not an extension of the exception type. So this would compile and print just nothing, because this block does not throw anything. So it would just execute and go away. Okay, I think we will look into the examples like this later on. Okay, so since Java 7, we have try with resources. Okay, we saw this already. So this is a try finally, we try buffered, etc. So any exceptions happening over there can be catched after this block, just like we saw with a normal try block. All right, so this is all obvious. So usage of exceptions should not be a subject of abuse, because, for instance, you should not be using exceptions for the flow control. Like here, you're just looping, iterating over the array and calling some function until you catch the array index out of bound exception. So basically, this should not be the style of program that you are using. This is because actually handling of exceptions is quite expensive operation for the virtual machine. So this is a bad style of programming. The good style of programming is actually avoiding exceptions as much as possible. Okay. Then another recommendation is avoid unnecessary use of checked exceptions. For instance, you are calling a method for the object, and this method might call the checked exception, right? So this is kind of okay. But if you expect some not normal situation, right, happening in the object, you should be checking beforehand this, and this is much cleaner code. So basically, if you are, especially if you are programming this object and you can check that everything is okay, all the conditions are met in order to execute the action, you should be doing that instead of just waiting for the exception to happen and help you. Okay, so these were my few slides about the exceptions. Let me, how do I, okay, like this. Let's check if I have any kind of examples. Okay, so I have some examples, hopefully. Let me execute a few slides here. So basically, print stack trace, this is a utility I have made myself, which basically prints the stack. It loops for the current method stack and prints it out, so we can visualize where we are. So this is a stack we're running at. And as you can see, there is a main method in the class remote execution control, right? So this is basically this kernel, Java kernel utility, and it has called multiple methods on a way until we got into the doit application, okay, into somewhere here, right? Okay, replication doit. Why it's called doing? Okay, so this is another example. We have a doit method defined, right? This is a doit method, and we basically loop it 5 times, right? 5 times, and at the end we just call the stack trace, right? So this is a call for the method. So basically, enter a method, go it. So doit is basically execution of this notebook block, right? Execution of this notebook block, and these are the executions of mine. So 1, 2, 3, 4, 5, right? 5 executions, and the 5th one basically prints. So what we have here is, again, the main method was called for the execution of this notebook, of this kernel, and then all the stack, and then at this location we just called whatever is need to be executed in this cell of a notebook, and then 5 times calling in recursion this doit method. As you can see, enter is if countdown is more than 0, right? So take 1 out and call doit. So basically call recursively itself for 5 times. And at the end, it just printed a stack. So basically, it entered this doit method recursively 5 times. All right, exception demo. These are various exception demos, I think. We have the first call, and it has the second call, right? So basically, first call, second call calls a third call, and the third call basically throws an exception, IO exception, right? And this is a checked exception, so it needs to be declared that it is being handled, right? It is being called from within the block. So basically, we can just try like this. And it is said that unreported exception, IO exception, must be caught or declared to be thrown, since it is being called right there. So we need to add it, and now it should compile. Yeah, it compiles. So basically, all these methods, first, second, and third, these methods are declaring that an exception is being thrown within the block. And yeah, so basically here, this exception is being thrown. So if we comment that line as well, oh, it's okay. It's okay. So basically, IO exception should not be called, right, from within the block in order to execute it. About this guy. Yeah. So the block itself cannot have the cached exception declared and not being thrown inside, right? IO exception is never thrown in a body of corresponding try statement, as you can see, right? But for the method, it's okay to have it declared as being thrown, but actually it does not. Okay, so basically compiling this, having the object specified, and first call. So basically, after we called it, we see the exception thrown, and exception has been thrown from the first call, second call, and third call. This is the actual stack of call. It called second called the third, and then the exception occurred. Okay. So this is handling. So we just not throw it away into the notebook. We just try to handle it somehow, right? So this is the handling. So we basically print the stack trace for the exception and print the class, right? So basically the class of our exception, the type of an exception, obviously starts from top down, starts from object, then goes to throwable, exception, and then checked IO exception. Okay. So first call 02 is just the same business, but handled everything in the method itself. Nothing need to be declared as thrown here, because we just handle the exceptional situation right there in the method. Okay, this is the runtime exception. So basically, we have a exception demo 03 demo method, right? It calls throwing, and what it throws, it just tries to divide by 0, right? It just tries to divide by 0. Okay, so basically we run it, and obviously it throws an arithmetic exception, which is division by 0 exception, right? So we handle it as a normal checked exception here. We catch it up, print out the stack. And now, as you can see in the object here we have object, throwable exception, and runtime exception, right? And under the runtime exception, we have an arithmetic exception. So this is the difference. Here we had a direct descendant for the IO exception, right? This was IO exception. That's why it's a checked exception. Here we have an additional item. This is runtime exception, and it has the arithmetic exception. Okay. So here we handled a specific type of an exception, arithmetic one, but we can handle a super type as well. Runtime exception, any kind of runtime exception we can handle, or we just can do nothing about it, right? It will be thrown, obviously, but we can leave it as is because we just don't need to specify that we are handling it. Just like here in this method, we did not specify that we expect the arithmetic exception being thrown here, nor we have declared it here. So for runtime exceptions, these are the special kind of exceptions where you don't need to declare that you are handling it, because they can occur just like that, division by zero. If you would be expecting these exceptions all the time, so basically you would have to declare everywhere that you're expecting the runtime exception and so on. So in order to avoid this overkill verbosity, it is not required to handle these guys specifically and explicitly. So basically, for this kind of situation, obviously, in real world, you have to check if you are dividing by zero or not beforehand, of course. This is just an example of runtime exception. Okay, and now an example for errors. So here we have an exception demo class where we basically simulating two things. One thing is we recursively calling ourselves, right, many times until the stack length is met, until we reach the length of a stack. And basically, once we reach the length of a stack, error type exception will be thrown, right? And obviously, this not need to be checked as well, because you just don't know when it can happen. And in application, it can happen anytime. So basically, again, not checked exception. Just like in out-of-memory example, so we have an infinite loop that basically concatenates a string. And once the memory is down, don't have any more memory, it will throw an exception, obviously. Okay, just like try to handle. I think this will crash my notebook, my kernel, but whatever. I will restart it. Okay, so running. Okay, so recursive demo, we basically filled out the stack, and as you can see, we've got Stack Overflow error, and this is an error exception. So basically, we have a hierarchy of object throwable, again, the same, just like in the normal exception, then error, this is a different branch, and then virtual machine error and Stack Overflow error. So basically, once our stack length met 70,490 items, so basically 17,490 calls of itself methods actually filled out with stack, and stack basically overfilled. Okay, and now the out of memory exception. So basically we will try to fill out the memory. Okay, and we just did that. So basically we have got an exception which has a name out of memory exception. Java heap space was wasted. So basically, again, we have object throwable error and virtual machine error, the same like with Stack Overflow. And here is a different kind of class, out of memory error. And the memory was filled when virtual machine here reached the limit was 512 megabytes. Okay. So these are the quizzes you've seen already, and I talked about these. So basically, IO exception will compile or not. No, it does not compile because nothing throws an IO exception inside. We can actually uncomment that to be precise. Yeah. And here, if it is the generic exception being caught, so this one just compiles and it's all fine, all good. Okay, these are just corner cases, not very much important. Okay, so masking exceptions, we have an example where we have a hierarchy of interfaces. So basically we have an interface of type 1, interface of type 2, an interface of type 3. And as you can see, all interfaces have a method f declared, right? Interface of method f declared, all the interfaces. And some exceptions are unique, right? So clone not supported exception, right? One of them, type 1, declares to be thrown. Type 2 declares an interrupted exception. Type 3 interrupt exception as well. And as well in array index out of bound exception. So different kinds of exceptions are being thrown. So, and we just combine 1 and 2 and 2 and 3 into the mixins, basically, right? So we combine it. And now what we have, we just basically implement the method and try to call it. Let's see what happens. Right. So basically type 1, 2, 1 and 2 was called without any problems, right? So basically we have received results. And now let's see about the combination of type 2 and 3, right? Type 2 and 3, these guys, right? We call it. And as you can see, it says, okay, man, I can't call this because you need to handle interrupted exception. So what happened, the common exception was accepted as the only throwable from within the method. If we are not the same exceptions, right? So basically we have thrown away. So in combination of interfaces on inheritances, so basically the common exceptions remain, and the exceptions which are unique for the interface method are being thrown off. Okay, and here, as you can see, it works once we have declared that we have a method which handles interrupt exception. Okay. Okay, these are some examples. For instance, a method decision, which basically try and final block. So we have return true and return false, right? So basically there's a question we need to ask either it return true or false, right? So we basically call it and it returns false, right? It returns false because everything is being executed at the very end. Okay. So these are the corner cases I would not be commenting, but these things rather should be avoided in using like that, right? Or you should know them because this is kind of unknown behavior. Exit, okay, system out print hello world and system exit, right? And prints goodbye world. So you just don't know which one will, what actually will happen. I think this is the place where my kernel will go down. Let's try. Hello world. It just basically prints hello world. And I think my notebook is down. Yeah, illegal state exception has been closed. Okay, in order to recover, I have to restart the kernel. Okay, because what was called is a system exit. System exit, and finally block was never reached now. Okay, I will not be executing that again because it actually breaks my notebook. Okay, so what you can do is you can create your own exceptions. So for instance, here is the checked exception, which you can create by yourself, right? So my exception, right? This is a constructor. So you receive a message, you can throw it up, you can have additional fields and whatever you want, additional behavior for this exception, right? So then this is a usage for the exception. You can tell that you are throwing some method, you are throwing that exception. This is what you actually do. You provide the description for your exception, right? And here in the calling method, right, you basically handle it somehow, right? So basically you can extend your exceptions and have them in your set of objects, in set of classes. My runtime exception. So as well, you can have your runtime exceptions, right? So runtime exceptions and errors. Yeah, so obviously you can have all of these specified for yourself. So obviously, as you can see, runtime exceptions are not being declared as being thrown. So you can basically use them as a normal runtime exceptions as well as errors. Unchecked. Static friends. This is again the quiz, which is in a corner case again. I think we have a friend, right? A class friend, which has an instance of itself, right? This is friend instance of itself. So it is basically declaring it. And what happens is that in the constructor, it basically throws an exception. Right? So basically, once it tries to construct itself, it throws an exception. So you would expect, I guess, that this actually class is never being constructed, right? So we can just basically compile it and try to construct at least one friend. And let's see what it will print. It will print a surprise that friend was constructed, or will it print I told you so, which is an exception thrown, right? Which you would expect, right? So, and what actually happens is the Stack Overflow, right? It tries to construct this instance variable so many times, right? It's actually throwing, and so on. And it's never finishes. So that's why we have an exception, but this is a different kind of exception, right? Unexpected. Okay, these are corner cases that most likely you will not meet while programming Java, but just for your illustration that there are interesting things. And okay, so I just shown you that there are 3 types of exceptional situations that can occur in Java application. And yeah, that's it. I'm just closing it up. So yeah, that's it for an exception. Let's move on. Okay, now we have a topic, IO streams. So basically in Java, in a classical Java, we have streams, streams for reading, right? For reading, you have a data source and you basically read the stream. And in a program, you basically construct an object that handles a stream of data. As well, for outputting, you have an object for the output stream. So basically input stream and output stream. One reads from the source into the application, another writes into the source from the application, right? So basically 2 notions, 2 objects. So most of the classes in IO package are associated directly with the streams, but some of them are not. So most frequently used, those are file, of course, which is a object which is associated with a file on the file system, obviously. Various file name filters, random access files, and so on are also possible, right, in this package. Okay, the lowest level of the stream is actually so-called the byte stream, where everything is being handled in the shape of bytes. So basically 8 bits. So whatever you're reading from the source or writing to the source is being treated as a byte. And this is the lowest level of the stream. So we have an input stream and output stream, right? So for instance, for the specifically writing and reading to the files, we have file input stream and file output stream. And these guys are working with the bytes only, right? So 8 bits at a time. So stream is some source of the data, some sequence of the data which unlimited length. So you just don't know what length it is, but you are reading byte by byte. And the lowest level of the stream is actually input and output stream working with 8 bits. Okay, so these are an example. So basically, try with resources, you construct the file input stream, right? You point to the file, you say that this is the file I want to read from. Then you can declare a file output stream. This is a file that you want to write to. And basically, then you loop until something is being available in reading from the input stream, right? And basically, everything what you receive into variable C. This is integer, this is 4 bytes, so that's long enough to contain a byte, right? So using a byte just specifically is not okay because it is signed one, but using an integer is fine because it's long enough. So basically we are reading until -1 is being met, right? So then basically you write it, this byte, into the output stream. And everywhere where you work with the IOs, classical IOs, you need to handle IO exceptions, right? Because IO exceptions are checked exceptions that are being thrown in various situations. For instance, file not found, file is not accessible, and so on and so forth. Stream has been cut, closed unexpectedly, and things like that. Everything is happening, and I/O exceptions are being thrown. You can handle these exceptions specifically, or you just can handle I/O exception, but you need to take care of that, because otherwise you cannot compile. Okay, on top of the byte streams, we have so-called character streams, and these character streams are working with the Unicode characters. Unicode characters are basically, in most cases, are constructed as 2 bytes, 16 bits. So basically, this allows to express various characters from the national languages, because you can expect that the Chinese language with something like 18,000 of characters would not fit into 8 bits, right? So that's why you need to have a much wider encoding system. So Unicode does that, and it's a variable length. So again, for the character streams, we have special objects, readers and writers. But the point is that these readers and writers are working with the byte streams inside, right? So they are just using these byte streams and just acting as a wrapper object, which decode and encode whatever we receive from the byte input and output streams into the 16-bit value. So yeah, so streams are constructed as a sandwich. So basically, higher level objects are constructed on top of the lower level objects or streams, as you can tell. Okay, so another type of streams we encounter in Java are basically buffered streams. So buffered streams do not handle elements of a stream one by one, but they are able to buffer, to basically read into some kind of a buffer and then flush it for the user or towards the source. So basically buffered input stream, buffered output streams, these are byte streams, but they are buffered. So basically you can fill up some kind of a memory and then you flush into the source or flush into the application, read to the application. The same happens with the readers, right? Okay, so this is what actually happens. You have buffered reader and buffered writer, the same thing. So what happens now is that you're reading lines. So basically your buffer is a line. So you are reading into the string, as you can see. You don't read character by character, but you already filling up a string until the carriage return is met in the input stream. And then you basically flush it out into the output, println. So it basically writes the line and puts in carriage return at the end. Okay, this is a scanner example. So scanner example is basically the an object which acts as a scanner for the input stream, right? So you have some kind of an input stream where you're reading something and you can declare what you are expecting to be the end of the input buffer, right? So basically you're reading everything into the buffer until some kind of a character is being met. So for the scanner, you can declare that this kind of delimiter in the shape of a regular expression need to be used. Okay. So formatting. So basically streams can be formatted in various forms. So just like that. So the square foot of D is F and so on. So D is the integer number and F is a floating point number. So basically you can format these and provide these variables as a formatting thing. So there are various conventions in how to format, and this is a subject of the IO package. Command line is treated as an input stream, of course, because you can read and write input and output stream. So basically, a console object works like this. A special type of the stream is so-called the data input and data output stream, right? So basically, these are meant for reading and writing primitive values like double, int, and strings. As you can see, UTF is considered to be a string, right? So basically, reading and writing primitive values and strings are possible in a sequence by using the data output and data input streams, right? But you need to know the order. By reading, you need to know beforehand in what order you're expecting these values to appear in a stream. Okay. Okay, this is just an IO package show up. So you can see that there are various objects, etc. So various classes, just like an input stream, for instance, we have an input stream and various types of an input stream, buffered input stream, and so on. So everything is being laid out like the sandwich, right? The generic input stream. This is an abstract, and then you have various kinds of input streams, right? And the same applies for the output stream. We have various kinds of output streams. Readers and writers are here as well. Okay. Okay, so let's go and take a look before moving forward into the okay, IO. We have here IO. Okay, print superclass. Just let's fill it up for utility. Helper method. Okay, so this is a byte stream. The example that I showed you before. This is a byte stream. So string builder. There is a string builder which we're about to fill in, right? A string builder is a mutable object which can be used instead of just strings because we can mutate that. So we have input stream, right, which will be reading from the file school.txt. And since this is an input stream, file input stream, this is a 8 bits, right, reader. So it basically reads into the byte. Okay, so basically it will read a byte, 8 bits, and will append the string builder. Okay, so let's try to do that. Okay, so it has read it out, and this is the content of what was read. And as you can see, there are some word characters which did not were possible to decode because we've been reading into the 8 bits and considered that all the information we need is actually within these 2 bits, 8 bits, right? And apparently, for instance, here you can clearly see that this is Jala, right? This is a single character, but it was treated as 2 separate characters, right? So these need to be combined into one Unicode character, right? So that's why it is a wrong way of reading some sophisticated national character bearing UTF source by using the byte stream. Okay, this is just reading and writing, I think, right? Yeah. So basically what happened, we read from the same school.txt and we wrote back. And as you can see, we are using the two objects. One is file input stream and a file output stream, and these are direct descendants of input stream and output stream. Okay, so let's do the same business with the read and writer. These are the character streams, right? With character streams, now we're reading not into the byte, but into the integer because this is much longer. Okay, let's try to read, and we expect that this one will treat the characters well. So as you can see, characters were decoded well. And this is from famous poem, right, about the rabbit school. So basically, with the national characters, we were able to read with the character stream now. Okay, the same stuff. We're just looking. input stream reader and file reader. So this is these two guys are descendant from the reader branch, right? Read and writer branch. Okay, so this is a buffered reader, right? These are examples for the buffered reader. As you can see, buffered reader acts just like the reader, so it's okay to read the national characters, but it was reading line by line, right? So again, buffered reader is just an extension of reader again. Okay, so this is an example for the scanner, right? So scanner is basically using the default as default delimiter is a space, right? So we can switch it. Switch that and use something else. So now all the punctuations like comma and dot is used as a delimiter. So basically we can see the difference, right? So we can use for instance, delimiter letter A, and as you can see, letter A was used as a delimiter, right? Okay, so this is a scanner. Okay, pipe streams. Okay, these are just combination of the streams. So if you want to while reading from the input stream, you want to write it directly to the output stream. Since I don't know which version of Java, you can use not this buffered reader in, buffered reader out, but you can use basically this chained pipes. So whatever you will be reading from one, you will be writing into the other. So this is quite convenient for copying data. Okay, so let's move forward. This was the demonstration of some I/O features. Okay, so I'm moving on with presentation. Okay, so along with the I/O things, actually, we have the so-called object serialization mechanism, where an object can be represented as a sequence of bytes, so that the object data now can be transferred over the network or serialized into the file and stored there. And after some time, it can be restored into the memory of virtual machine. So this mechanism is called serialization. So and of course the process of transferring object from the memory into the bytes, into the sequence of bytes, is called the serialization, and the vice versa inverse process of reading from the file or the network sequence of bytes and writing into the correct format into the memory and being able to handle as an object is called a deserialization, right? So basically, making a class serializable in Java is very easy. You just need to declare that your class implements Java I serializable, of course. And there is a special field, static, obviously, field that handles versions. So basically, once you have declared your class as being serializable, so you expect it to be serialized, written into the file, for instance, right, for transmission, for copying, and deserialized later on, you have to put this private static final long serial version UID and say which version your class is in. Because once you will be deserializing, Java Virtual Machine will check if it is the same version for the class. All right. So basically, serializing and deserializing objects is being handled by the object input stream and object output streams, right? So this actually happens just like we did with the characters, the strings, and primitive things, right? So basically, you declare the location where you will be writing file to. So this is a file output stream. and you provide this as the source, the target for writing the object into the object output stream. And then you just say write object and provide that object, which is item class of item class. And reading just the same, you declare the file input stream, right? And then you read the object. Okay. Okay, if you want to handle the object specifically, for instance, you just want to write some specific parts of an object, not everything, right? You can skip this with a special annotation, or you can implement the private method, private void write object method, which receives the object output stream, and you can write in the order you want, right? And there is a possibility to write your own version of read object, where you receive the object input stream and basically write the data from fields in whatever order you want. Okay, so basically there are some culprits for using visualization in your classes, because it is said to decrease the flexibility to change a class implementation, because if you are using visualization, you should understand that someone might have the serialized version of the class, and if you would release a new version of the class, it might not be able to handle the previous one, right? Increases the likelihood of bugs and security holes. Of course, when the class is being serialized into the file, it can be tampered, it can be changed by somebody, right? And when you will read it back, you can read some different data. Testing burden, of course, is being increased. Okay, and there are customized realization methods. Immutable class contain private mutable composite. Okay, these copying things and so on. So, okay, so there are some bad things about the serialization, which is said to be avoided, right? And I've met a bunch of projects in industry that do not use serialization at all. And when I asked them to include serialization for their library classes, they told no, we don't want to do that. And this is quite normal. Okay, now all outputs clear. So this is an extended example of serialization. So basically what we have here, I think we have several implementations for the serialization. So we define an interface writable, where we declare a couple of methods, write and read. This is our own version of serialization. So basically we compile this, right? Now we have a utility methods. Utility method basically for writing. It takes the file, the destination, and it takes unlimited set of objects. So this basically becomes an array. This type of notation in Java tells that you can provide 0 or many objects, and once it's received, you get this W as an array, right? So we can basically iterate over it. Okay, so this basically helper method that just lets us to write objects into the file. Okay, so, and obviously this W, right, this W, as you can see here, is generics, and you expect that W is of type writable, right? So obviously it has methods to write and read. That's why we need to declare this interface, because we want these objects that we're about to write into the output stream or have these methods declared, right? So this is one thing for writing, and another thing for eating. Remember when we were talking about the generics, I told you that we can't initialize a generic class like this. Generic class like a new instance, right? So the common technique is actually to pass the class here along with the as an argument into the function. So this is actually happening here. So for reading for reading objects from within the data file, we have to pass the type in which we expect to be stored in the data file. So we basically compile. And this is an example class. It's product. It has a name, unit price, and stock, right? And it's writable, obviously, right? So we basically, in a constructor, we have a default constructor, and default constructor is required because we will be constructing here the new instance without any parameters, right? Without any arguments. So default constructor is required, and this is very common in serialization. Okay, so but for our convenience, we have a overloaded constructor where we just provide all the field information inside, right? We have a write and read methods. So basically, writing accepts the data output stream and writes name, unit price, and stock. But for reading, data input stream reads from the input stream with name, unit price, and stock in the same order, right? Okay, so we basically compile this. We did create a few objects. So we create a few objects, Pienas Sviestas, right? And now we just basically can print our stock in the store, right? And now we can write these guys into the file, right? So we call our helper utility method write into the store.dat, right? So we can check store.dat, right? And this is a binary file, right? This is a binary file. We just wrote our data into that. 46 bytes, right? So we can basically remove that and make sure that we did it, right? So basically writing again and going back, and you can see store appeared, right, seconds ago. Okay, we just wrote our data into the file, and now we can read data from the file, right? So basically reading product class from F, and F is a stored dat, right? Store one, and as you can see, we just read it back. So this serialization method and this technique is using data streams. So these are primitive types plus string, right? So we have implemented the mechanism of ourselves for ourselves manually, right? And here is the serialization by using object streams, right? So we have a few helper methods defined for reading from input stream, right? We just provide an input stream, and we read objects, right? We read whatever objects we have and return it. Read object. Read a single object. Okay, read a single object, and here write an object into the output stream. Okay, so we basically can specify it. Read from bytes. We can read and write to the bytes. So basically, this is array of bytes. We will be serializing our object to and from. So basically, we can provide a set of bytes. Okay. And these are files. These are files. We are reading and writing to the files, just the same thing. Okay. So these are definition of some classes. We have an engine defined here quite extensively, right, which has a fuel and volume, a couple of fields, right? And here we have a car which has an engine, right? And as you can see, engine is declared to be transient. So let's remove that for the time being. Let's make it clearer. Okay, so basically we have engine, which is not serializable, right? And we have a car, which is serializable, right? So let's see what happens. So we have declared ourselves a car, and this is C, right? This is name Fiat, year 1998, color blue, and engine. It has a petroleum engine, 1.3 volume liters, most probably. Okay. So basically now we can, okay, this is a write to file out.dat. Let's remove it right now. That, remove it. And just let's remove it. Okay, so let's write it to file. Right, not serializable exception. So it basically complained that there is an object in a chain which is not serializable, right? So we can do one of the two things. I would declare of engine to be serializable, so it will be serialized in a sequence, or we can say that it is transient. So basically, we will not be serializing this chain, right? The engine. Okay, let's do it like this. Okay, write to file. Okay, now it worked. So we basically have wrote to the file, right? And now we can read it back. C1, right? Just read it back. And C1 is null. Why it is null? Car that C. Okay. I have not declared it, right? I have not specified it. Okay, my Fiat. Write to file and read from file. Okay, I just read it back. So basically, I wrote this car into the file, serialized it, right, and read it back. And as you can see, engine is null because we declared this to be transient, right? In order to be able to store engine, we just need to remove transient, right, and say that it implements serializable, right? So basically, all the classes that are going into the file, into this data stream, has to be declared as serializable ones, right? So these two things. And now again, my car. Okay, these two things I will talk about later. Writing to file and reading out from file. And now engine is actually read back from the file. So now in the sequence, it was written into the file and read back. Okay, now we had our implementation of the class, right? Our version of the class equals 1, right? What if we would change this to 2, right? Okay, to 2, 2L. Okay, so now let's imagine we have changed our engine, right? Class slightly, have modified it, so we declare it, and now try to read it back, read from file, right? And we've been able to read, I think, and this is because of notebook. Let's try to restart the notebook, okay? Because the previous version remains in the memory. So kernel ready. We need to specify these methods a little bit, okay? Kernel restarted. Okay, so this is definition of my classes. Okay, we'll not do that and just try to read it back. Okay, so what it says, class not found exception, right? So it did not find the right class. Read from file. Yeah, class not found exception. Okay. It is here. The car is here. The car I can implement. Okay. And read from file. It's not found exception. Okay. I think this is related. I should have gotten the different kind of exception, and this is related to the notebook. In the notebook, once declared, you cannot redeclare the class. And I think that the class that was actually declared and has gone into the file is of different flavor. So basically, in notebooks, I cannot show this example right away. Yeah, but the point is that if I change the version UID for the class. I basically screwed up my stored classes and I cannot read it back because it will be checked that the version UIDs are the same. Okay, so I can't show to the full extent this example by using the notebook. So that's the story. Okay, so how many slides do I have? I have them a lot. I think that new IO we just can go through still. Okay, so let me continue with IO. So basically, we've seen the streams, inputted out streams, various flavors, serialization. So the new IO since Java 1.4 quite a while ago, we have a new objects for reading and writing into the streams. So we have a channel IO, and we have streams. We have channels instead of streams, and these channels are coupled with buffers. So basically, we have buffers, and we are reading from channels into the buffer and writing from buffer to the channel. So basically, we are communicating via buffer with the channel. And the difference is that this I/O, in contrary than with the channel I/O, is a non-blocking I/O. So basically, you can have simultaneous reading and writing into the channels, not like with the previous thing, right? So this type of I/O is more ready for the multi-threaded environment. Okay, so basically this is a notion of channels. So you can both read and write to the channel, right? So streams are just one way. As we've seen, we have to have a separate object for reading and writing. And for the channel, you don't need to do that. You just have a channel and you read and write into these. Can be read and written asynchronously, right? Channels always read to or read from the buffer. So basically you have an intermediate object which you communicate with the channel, right? And there are various implementations: file, datagram, sockets for the TCP channels, right? So basically communicating over network. Datagram is for UDP protocols, communicating in the channel and things like that, right? So basically you declare channel, and then after doing so, right, you have a buffer, and basically you communicate with the channel via your use of the buffer, right? So there are a flavor of buffers. So basically, when you need to interact with the channels, you have to have a buffer again. So basically, yeah, so transfer to, transfer from. So to the buffers, there are various buffers: byte buffers, map by buffer, character buffers. You have already some hint about what's the difference. One is working with bytes and working with Unicode characters. Double buffer, float buffer, these are specific data types: long buffer and short buffer, right? So basically you declare the length of the buffer, and basically when you're reading, you can rewind the buffer, because the buffer has a pointer where it's actually looking at, so things like that. Okay, so basically, again, the difference is that stream IO via buffers. So we have streams and buffer is a more convenient way because it does not require two objects for reading and writing. Streams are blocking. You can have blocking things in new IO as well, but in new IO you can have a non-blocking behavior. So basically, while reading, you can just basically, if nothing is to be read from the channel, from the buffer, from the channel into the buffer, right? You can basically do something else. You can go and loop. You can do something else instead of just blocking your pointer, your thread on the reading point. Okay. So application design: one thread, one stream. So basically with IO, you have to dedicate a special thread for working with a single stream because it's blocking, right? And for new I/O, you can have one thread working with multiple channels and multiple buffers. Okay. Okay, so new I/O actually features some additional good things. This is basically these are various basically utilities to work with file system. There are a bunch of static and not so static classes. So, for instance, the most important class is actually the path, which points to some path object like a folder or a file or something else which can reside on a file system, right? So then you have file system class and some other classes which are basically utility classes which cannot be initiated, but they are used for utility methods. Okay. Okay, so basically with paths you get a path object, and with path object you can do a lot of things, right? So for instance, you can print it out, you can get file name, get name count, subpath, parent, etc. So lots of good things. With utilities like files, you can check if it is a regular file, it is executable, readable, etc. With files, you can create directories, delete directories, and so on, copy files, etc. So this is very convenient and for your convenience, right, for your usage. Okay, let's take a look if we have some notebook about the new I/Os. Okay, so let's take a look what's in there. Okay, so basically random access file. So basically opening a file again with school, we have a channel declared in channel, right, which we'll be reading from, and we are reading into the buffer, and until buffer has not finished we basically loop it up. I guess this will be reading from the buffer. Yeah. Okay, and since this was a byte buffer, right, a byte buffer, so we did not have a possibility to actually encode it, right? So this is again the same thing. We have a byte buffer, but here we have a decoding utility, the charset, right, which we will ask to decode our buffer content. Right? So basically, this decoding utility basically decodes the Unicode characters correctly. Okay, the transfer. This must be reading and writing to, right? So number of bytes that was transferred from one file into the other. Okay, something like that. And working with a file system is basically something like this. So you can get the current path. You can look into the absolute folder. So something like this. Okay. Paths, you can get bunch of information about your file system. Okay, so this was the new I/O. And I think we should not be going into the reflections because we will have plenty of time next time. So we will start from the reflections. Okay, so that's it for today, I guess. Unless you have any questions, we can close the recording. Okay, I'm basically stopping the recording.